So I'm now going to move on to our second speaker of the session. And so it's a bit of a change of pace. It's a piece of research that will be presented, if I'm not mistaken, at NeurIPS next week in one of the co-located workshops. It's a workshop that's called ENLSP. And so we have with us Mohamed Nabih Ali. He is a research associate working in FPK in Italy, I believe. And he is going to present to us this piece of work, which is named FedEE, and it is an ASR model where the underpinning architecture has these early exit characteristics. This model is also federated, and so these two things working together can enable some pretty powerful scenarios. So with that, I'm really happy to hand over to Mohamed.
Okay, I'm Mohamed. I'm a postdoctoral student at Fondazione Bruno, Kessler, Italy. So I'm doing my research at Speech Tech Unit here. And today I'm going to present our recent work on heterogeneous federated learning for automatic speech recognition using early exit architecture. So this work is recently accepted at NLSP workshop, will be hosted in NeurIPS, which will be held next weekend. So for the next slides, I will be a little bit quick because it is a well-known information about federated learning. So basically, what is federated learning? It is a kind of a decentralized approach for training machine learning architectures to ensure data privacy and security. So basically what happens during federated learning? So firstly, there is a server which instantiates a random global model. So during the federated learning rounds, so a random set of clients are choosing to participate during the federated learning round. Each client perform local training for certain number of epochs on its local data, and this data should not be shareable between all clients. So after this local training epochs, the server accepts the trained weights from the clients and aggregate it to generate the new global model that's sent back again to clients for the next round. And this operation is repeated for many rounds. So basically, there are many aggregation strategies that can be done on the server side to aggregate the weights come from the selected clients for training. So the most two popular aggregation strategies, the first one is federated average, when the server averaging the weights of the clients to generate the new global models that's sent back again to the clients for the next round. Or the next one is FedAdam strategy, when after do the averaging the weights, you apply a gradient optimization on the server side before send the new model to the clients for the next round. So I focus on these two strategies because later I show you our experiments, we address these two strategies. So federated learning has many challenges, like how to handle the connected clients during each rounds. The data that is used to train the clients, maybe this data is not homogeneous. So the data had a lot of statistical distributions. For sure, you need to ensure the privacy of data. You cannot share the data between the clients. But in our work, we focus on model heterogeneity, when the clients cannot share the same architecture during training. Why we choose model heterogeneity in our work? Because most of the state of the art, especially for speech recognition, are using the homogeneous federated learning scenario. So basically, the server model and the clients share the same model architecture, and they do the normal federated learning scenario, as I explained in the second slide. So the server sends a model to the clients. They do local training for certain number of epochs, send the weights, aggregate using any aggregation strategy, and then send the new global model to the clients. In this scenario, you have for sure pros and cons. So the pros of this scenario is that you can aggregate the weights of the clients in a straightforward way using either, for example, Fed average or Fair Adam or any popular aggregation strategy. But the con of this scenario is that you don't consider the computational complexity and the computational resources of the clients. So because you share the same model, so maybe you have some clients that has low computational resources and they cannot fit the server model. So to tackle this problem, there is a kind of heterogeneous federated learning. So in heterogeneous federated learning, I here focus on heterogeneous architecture. So there is a kind of heterogeneous data, but in our work, we focus on architecture heterogeneity. So in heterogeneous federated learning, it is a crucial demand because the popular development of edge devices, wearable devices, and etc. So you need to be sure that your model can be adapted on these devices. So you cannot train large model on these devices. So basically, what happened in heterogeneous federated learning, so you have a server model, but the clients not share the same architecture of the model. And in this way, you need to find a way to aggregate the weights because the architectures are not the same. So as you can see here, for example, in step 3, you need to aggregate the weights using at least some common information between the server model and the client's model. So in the state of the art, let me focus on architecture sharing. Yeah, this is a kind of solution. In order to tackle the problem of architecture heterogeneity in federated learning, as I said, you need to find a common part between the server and the client's architecture. So either you can share the backbone of the model, or you can share at least the classifier, or you can choose which part you need to share between the server and the client. And then you can aggregate using some approaches like knowledge distillation, transfer learning. Here, I give you a little bit graphical example of what I mean in heterogeneous federated learning, especially if you address the architecture heterogeneity. So here, for example, you have, this is the global model, the server model. You have different clients, for example, 3 clients. The clients have different architectures, but you only share the classifier layer and the last layer. So you share only the classifier layers. And this is quite challenging because here you need, first, you need to a little bit expert how to select the architecture that can fit your client, because not all clients have the same computational resources. So you need a little bit to sure that your model adapts the clients. Then which part you can share with the global model. So you can select the classifier or the backbone or any other part. So you need to be aware which part you need to share. The third challenge is that you need an articulated aggregation strategy, because you are not sharing sharing all the weights. You are sharing the common part weight. So it is a little bit challenging. So our solution to this problem is to use early exit architecture. So this is what we mean by early exit architecture. So basically, what are the early exit architecture? So it is a kind of adding some early exit points to the model architecture. So it is easily to decode or classify the input features based on your resource computational complexity. So you can decide at which point you need to decode your input or you classify your input. So here is an example in subfigure B. So this is the model. We introduce some early exit points. So if you have low resource computational device, you can only train the first part of the model, the more computational power you have, so you can train more layers in your model. So in this way, you can aggregate the model straightforwardly using the aggregation, the affordable aggregation strategy, like for example, Fed average or Fed Adam. You don't need to design specific model for each client. And then you also don't care about which part you share with the server global model. So to handle all of this situation, we are for sure using Flower that provide all the implementation of the aggregation strategy, client server connection. And with some few lines of code, you can federate your model. And according which deep learning framework, you can adapt the Flower to your framework. So let's go quickly to our experiments. So the model that we were using for federated learning is an early exit conformer layer. So this model has 12 conformer layers. In this model, we introduce 6 exits. After each two layers, we add a decoding bus, a decoding exit to form 6 exits. This model was pre-trained on LibreSpeech 1000 hours dataset. So it is interesting to know why we use a pre-trained model, why we didn't start from scratch. So we did some trials to start federated learning from scratch, and unfortunately, the model struggled to converge, and the word error rate approximately near 100%. So it is quite difficult to start from scratch. Then it is quite interesting to see if we start federated learning from out of domain data. As I will say later, we do federated learning based on another data set. So our pre-trained model was done on LibreSpeech, while when we start federated learning, we do federated learning on Tedlium-3 dataset. So we have a pre-trained model trained on large dataset, 1000 hour dataset, LibreSpeech. We do federated learning based on Tedlium-3. So to simulate real world scenario, we have approximately 2000 speaker in Tedlium-3 dataset. Each speaker represent one client. And we test the aggregated server model based on the test data of Tedlium-3, which has 16 speakers. Okay, for our next experiment, we consider 2 scenarios. The first scenario is homogeneous federated learning, when all clients train all exits of the model. And the second scenario is heterogeneous federated learning. So some clients train only the first exit, some clients train the second exit, some clients train all exit, and etc. So we have various clients train exits uniformly. So this is some results when we compare Fed average against Fed Adam versus Fed Adam. So in all these 6 sub-figures, this is word error rate for all exits versus number of rounds. So what is interesting here, Fed average is widely using in the state of the art, especially for speech recognition. But here, as you can see, Fed Adam outperforms Fed average. It helps the model to converge faster. So it is more effective than Fed average. Then the most interesting thing here is that even if we use heterogeneous model, not all exits are trained, the performance is not deteriorated. We reach at least similar performance, or maybe no notable deterioration in the performance. So this is quite interesting that Fed Adam performs better than Fed average. This makes us investigate another approach, which is freezing the convolutional front end. So instead of training the full model, we freeze the convolutional front end, and we train only the encoder and decoder part of the early exit conformer model. So here is the result. We compare the normal Fed Adam and when we freeze the model convolutional part. And it is quite interesting that we don't lose performance, but also we improve the performance a little bit. Small deterioration in the performance if we use heterogeneous model, but it is a little bit small. We don't lose a lot of performance when we use heterogeneous federated learning. We want to investigate more real scenarios in which, what if we have more edge devices clients? So most of clients has low computational resources. So what could be the situation? So we consider two use cases. We call it non-uniform and non-uniform extreme, where most of clients are generated to train the first exit only. So as you can see here, the distribution in case of non-uniform, 40% of clients are generated to train the first exit, while other distribution to generate other exits. And the non-uniform extreme, when 80% of clients are generated to train the first exit only. So as we expect that, in case of non-uniform extreme, the word error rate of the first exit converges faster with respect to non-uniform and with respect to uniform distribution. For all other exits, okay, the performance deteriorated a little bit because we don't have enough clients to train all of these exits. And the most interesting thing for the first word error rate of the first exit, that it improves because most of clients, okay, generated to train this exit, and this exit is always present in all clients. So if you generate a model that train all the 6 exits, for sure you have the first exit, so this exit also train in this situation. So it converges faster and you don't lose performance. Finally, we consider another training technique. It is called server central training. In this way, we fix a data set on the server side. We call it held out data set. So after aggregate the model on the server side, before sending the model to the clients, we do a kind of training on the server side. So to use this approach, we use the development set of Tedium 3 data set, and we do some local training on the server side for certain number of epochs, 10 epochs. And unfortunately, this approach doesn't help. So as you can see, we limit this experiment to only Fed average strategy. So as you can see here, there is a kind of overfitting when using the central training. And the key concept behind this approach is that when using the central training, you need to be a little bit aware which data set you use. So the development set of Tedium 3 is quite small data. So when you train for many epochs on the server side, maybe it introduced a little bit overfitting of the model. So as you can see, the model struggle to converge, it a little bit start to overfit. So here, the solution of this is use a small number of epochs on the central side, or try to use a larger data set for training. But we prefer to use all the affordable speaker in Tedium 3 for federated learning to help the model to converge faster. So finally, where we are. So this is our model, the early exit conformer model. This model, as I said, trained on 1,000 hour Libre speech dataset. We want to be sure that the model is a strong baseline. So when we test it on Libre speech test clean, it achieved the state of the art, as here in the first column. So the performance of exit number 6 is around 50% word error rate, which is a strong baseline. When we test it on Tedium test dataset in a normal central experiment, normal central training experiment, of course, the performance deteriorated. And from this point, we start our federated learning. So when we do federated learning for a heterogeneous model, freezing the convolutional front end, we improve the performance, especially on the first exit. We are a little bit quite near to the baseline, a little bit far from the baseline on other exits, but you need to be aware that we're starting from a far point. We're starting from out of domain data. We start from a model that is trained on libre speech and try to do federated learning on Tedlium. So we improve, but we are a little bit still far from Tedlium performance. So when we train the model based on Tedlium 3 and test on Tedlium test set in a normal central training, the performance is around 14.6. So we're a little bit far in our federated learning experiment. So maybe we can do some experiments using other model aggregation strategies that can help the model to converge faster. To conclude what I say, so we show that early exit model can allow federated learning in a heterogeneous scenario in a straightforward way. So we experimentally confirm that pre-training model is crucial needed to start federated learning, especially for speech recognition. But the role of central training on the server side is not crucial. You don't need it. The model can converge without it. Finally, we show that using Fed-Adam aggregation strategy in combination with freezing the convolutional front end helps the model to converge faster. So more details, you can find it in the paper. You can scan this QR code for the paper and this QR code for the code. It is available on GitHub repo. You can have a look on it, and time for questions.
Excellent. Thank you so much. That was really excellent. We can see if there's any questions from the audience, or I can look in Slack and other places that people sometimes post questions. But first, any questions from people currently here? So yeah, so one question is just asking about the generality of your methods. So you showed a lot of work on speech, but do you know if they will work well on image or other kinds of data types? I think they're just asking just out of interest to see what you think about that.
Because most of our research is done on speech processing. So our unit is called speech tech unit. So we are focusing on investigating different approaches that can help our research in speech recognition, intent classification, something like this. So it could be applied on other tasks for sure, but we only focus on speech as it help in our work.
I see. No, I think they're just seeing if you had ideas of how well it might work on other data types. But I suppose you only really know how well it will work on the speech ones.
That can be generalized.
For sure. The approach can be generalized to any kind of data. So what happens in speech can be applied to image, other types of data. So this approach is not designed for speech. So you can adapt the conformer model to for image classification, any other tasks.
Okay, cool. Let me see what else we have. Oh yes, so it seems like people will be interested in using it, and their question was related to that you mentioned there was some open source code. Is it really useful for just replicating the results in the paper, or could the code be used to perhaps build a functioning system where somebody wants to do ASR but using these types of methods?
Okay, I think it is available for both. So if you want to replicate the performance that we achieved in the paper, it is okay, because the both data sets that used for pre-training and federated learning is public available. So you can pre-train a model on libre speech and do federated learning on Tedlium. So you can use our code to replicate our results, and then the code is modifiable. So you can change the early conformal model. You can use another model. You can change your training strategy. You can change even if the decoder. So we are using CTC decoder. You can use other types of decoder. Maybe it helps to converge faster or improve the performance. So yeah, the code is modifiable. So anyone can try, can substitute some parts, etc.
Excellent. I see. Yeah, well, I mean, I guess one final question just for myself personally. I was curious about where you might go next with this work. What would be the next logical step that you might take? Do you want to to have bigger ASR models, or is there a different type of challenge you want to solve and combine it with this one together? Where do you see things headed?
Okay, we have different plans for our next research. So one possibility and the easiest one is to investigate the performance of other models. So now the current trend is to use self-supervised model. So the powerful of self-supervised model is that it can learn the capture of speech easier than conformal transformer model. So we can use self-supervised model in flavor of early access. So we can introduce we can replicate what we did but using self-supervised model. Another possibility is to use parameter efficient transfer link. So we can use something like adapters, prompt tuning, some other strategies we can integrate it inside our code, so we can investigate what happens when we use it.
I see. So using some of these prompt based methods or these fine tuning methods like that we've seen for large language models, but being applied to in this setting.
Yeah.
I see. Interesting. Great. Well, thank you so much.